Hi everybody, this is an introduction to this week's lab, which is called Air Track Projectile Motion PNW. So hopefully you've logged into pivotinteractives.com. You've logged in, you see this. We're going to be doing the projectile motion lab. So I'll just hit view. And it looks like this. Let's just read a little bit of this for you. Galileo performed a famous experiment where he used a ball rolling on a ramp, which you've also seen in Chapter 3, to study the motion of objects under the influence of gravity. The ramp allowed him to make more precise measurements because the ball moved more slowly on the ramp. So Galileo, as it says here, was able to dilute the effects of gravity when we were on the ramp. So on a ramp, the effects of gravity, it was less than 9.8 meters per second squared. So this, what you see here, is a hockey table, an air hockey table, that's been tilted on its side, and you're seeing an overhead view of it. So in doing so, this will simulate projectile motion. So remember, for projectile motion from Chapter 3, the x velocity stays constant. It's the y velocity that changes. So we won't have negative 9.8 meters per second squared in the y direction here. It'll be something less than that because this is not in free fall. So it looks kind of like this. You can just leave it at 30 frames per second. And you see a string down here. A hockey puck's going to fall and bounce over Einstein on this inclined plane. Okay? Excellent. So what we're going to do is take some data while this is looking like projectile motion. So after it leaves the string, let me back it up again, and while it's in the air. So I'll just advance it a little bit here. So I would wait until it leaves the string. Okay, so we'll start taking data after it leaves the string, and then while it's going over Einstein's head. And that will simulate projectile motion for us. Okay, so let's take a look at the tools that we have here. We've got a grid, so we'll use this grid. I'm going to back up the video to where I want to start. Again, I want it after it leaves the string. I'm going to put that as my 0, 0 coordinate. Okay, on the string, left the string. Okay, so let me make this 0, 0. Okay, something like that. And then I could use my clock here. So right now, for my data table, I have my first data point. 0.9 seconds, I'm at 0, 0. And then let me go to the next point. So what you want to do is have the time increase by 0.1 seconds. So although I've gone to the next frame, I don't want the next frame. I want the time to be 0.1 away from that. So 1 second. First data point was 0.9 seconds. I'm going to go up to 1 second. You want to leave these evenly spaced apart. So I had to hit this button a few times to do this. So although there's nice data here, to be able to make a velocity graph, we have to have these time increments evenly spaced out. So my second data point then will be 1 second, and then whatever this x coordinate is, whatever the y coordinate is, we can put that into the data table. Okay, so read it carefully. You could actually hit this and make it bigger. So what does a data table look like? Well, right now we've only got 5 rows here and 2 columns. We need another column, so let me add another column, insert column to the right. And I was playing around with this earlier. Let me change this to Y. Let me change this to X. And then, make sure you put the units on, seconds, and then we'll use T for time, units, centimeters, X, same thing, centimeters, Y. And you can be more descriptive if you want, like X coordinate, Y coordinate. Maybe that would actually be better. Whoops. Coord. Okay, so I'll leave that to you. You can clean that up. Okay, and then we're going to need some more rows. So get at least 10 data points. And again, make sure that you space them out by 0.1 seconds. So don't do any data in between that. So and the way I'm doing it, 0.9, 1, 1.1, 1.2, that sort of thing. Okay, and again, what I'll have to do here is hit it 1, 2, 3 times to get up to 1.1 second. There's a coordinate. 1.2, then you have that coordinate. Excellent, all the way back. So make sure you get the data on the way up, also on the way down. Not quite to the peak yet. Looks like we're getting close though. And then on the way down. You do not want to get data after it hits the string again. So another 0.1 seconds. You want to have these all 0.1 apart. So if you only take 10, you might not get all the way over to here, but you don't have to do 10. You can do more than 10. It doesn't take very long, actually. Okay, and then to add some rows, you can click here, insert rows below, just like we did before. Okay, so what you're going to do then is make position versus time graph, and difference this week is you can include both the x and y velocities on the same graph. Okay, so let me just make up some pretend data here. 0.9. And again, this is not real data. I'm just making some things up here. 1, just to show you how it works. 2. And then I'll do 1.1. 2. This, again, completely made up data. Just to show you how the graph works. Okay, so like we did before, on the horizontal axis you want to put the time. So what do we want to put there? Time. Okay, done. And I didn't include uncertainties in this lab. There's a lot of graphing to do, so I didn't do the uncertainty part. On the y-axis we want to plot, or I should say the vertical axis, we want to plot the x-coordinate. And then I also want to plot y, so I can do add columns, and then y, and then done. Okay, so now both sets of data are on the graph. So that's how you go about adding both sets of data. Okay, now you can also, like we did last week, do curve fits, and you could do a curve fit for both the x and y data. So refer back to what you did last week. Excellent. So use the resulting graph to describe the horizontal and vertical motion of the puck. And does this motion match what's expected for a projectile? And then explain. So, make sure you answer that question. So once you construct this graph, that's 10 points. And then down here, answer this question. Okay, and then we want to make a velocity versus time graph. So the data that we took, this data is position versus time data. We have to, on our own, come up with the velocity data. Luckily, we could use the position versus time data to pick out the velocity data. So the way that you do that, you'll have to watch this video because you're going to have to use your own data. Let's see. Making a velocity versus time graph. So make sure you watch this video. I'll open it up. You can see what it looks like. Here's where it's spelled out in words, and then here's the video you can watch. So essentially, you have to have the position versus time graphs, and then from that, you can go and use pivot to find out what the velocities are. So you have to watch this video. That's the way that you come up with the velocities. Okay, let me go back here. So same thing, you'll have to insert another column here, several more rows. Now, when you watch the video, you'll see that there won't be any velocity data for the first or the last row. That'll make more sense once you watch this, so I can't stress it enough. Make sure that you watch this making velocity versus time graph. Okay? So after you make the velocity versus time graphs, make sure you go back and then reset this position versus time graph to how it was initially. Okay. And good. Then you'll have the velocity versus time graphs, both of them again on the same graph. So what does the horizontal velocity versus time graph for the puck does it support your claims about horizontal motion? Why and why not? So, support whatever conclusions you come up with. From your graph, how much is the vertical acceleration? So remember, when you have a velocity versus time graph, the acceleration is the slope. So that's how you can figure out how much it actually is, both in the x and y direction. And then the part down here is, now that you've figured out the acceleration in the y direction, what angles does that correspond to? Okay, very good. All right, have some fun with it. Again, make sure that you watch that constructing velocity graph, and email any questions. Have a good day.